Have you ever actually stopped to think about what happens the second you turn the key or push the start button in your car? I mean, unless it stubbornly refuses to start on a freezing cold morning, it's pretty easy to just view the internal combustion engine as this heavy block of metal, right? Just a utilitarian machine that gets us from point A to point B. But the reality? The reality is far more fascinating. Welcome to this explainer. Today, we're going to unpack the internal combustion engine for what it truly is. An absolute marvel of synchronized engineering. We're talking about an incredibly precise mechanical symphony that literally harnesses thousands of controlled explosions every single minute just to power our lives. So let's dive right in and break down how this incredible orchestration actually works.
So here's our roadmap for today. First, we'll look at the core anatomy, the crank and cam. Second, the fuel fight, carburetors versus injection. Third, the ignition battle, petrol versus diesel. And finally, Section 4, beating the heat with cooling.
All right, let's kick things off with Section 1, core anatomy, the crank and the cam.
Let's dive right into the absolute core of the engine, starting at the very bottom of the block with the crankshaft. Think of it this way. If the engine is a living, breathing entity, the crankshaft is its heartbeat. Here's the crucial thing to understand. An engine's pistons move violently up and down, right? But your wheels, well, they need to spin in circles. So the crankshaft acts as the foundation for all this movement. It takes that linear, up and down energy from the pistons and brilliantly converts it into rotational power. This is the literal connection between those fiery explosions inside the engine and your tires finally hitting the pavement. And through its connection to the flywheel, it makes sure that the raw energy from the cylinders is smoothed out and transferred onward to the transmission, ultimately driving you forward. Now, if the crankshaft is the heartbeat, then the camshaft is the engine's rhythmic lungs. Usually sitting right up top, it meticulously controls the engine's breathing. It dictates the exact valve timing. What that means is, it regulates exactly when the intake valves open to suck in fresh air and fuel, and exactly when the exhaust valves open up to push the burnt gases out. Make no mistake, if these lungs don't breathe at the exact right microsecond, the entire system just completely collapses. And here's the crazy part. These two vital components don't just work together, they are locked in a perfectly timed mechanical chain reaction. As the crankshaft rotates at the bottom, it drives a timing belt or a timing chain. That belt or chain then travels up to turn the camshaft, which physically pushes the valves open and lets them close. It's like a finely tuned dance. They absolutely must work in perfect, locked harmony. Because if this timing is off by even a tiny fraction, well, the engine's going to suffer from misfires, a complete loss of power, or in some really bad cases, catastrophic internal collisions between the pistons and the valves. And you definitely don't want that.
Okay, moving on to Section 2, the fuel fight, carburetors versus fuel injection.
All right, so with the core moving parts in perfect sync, the engine obviously needs to eat. And for decades, there's been this massive engineering divide in exactly how we mix the air and fuel. On one side, we have the carburetor. This is an incredibly clever, purely mechanical device. It relies entirely on physics, specifically something called the Venturi effect, where air rushing through a narrow tube creates a sudden pressure drop that literally sucks fuel right out of a float bowl and into the airstream. Pretty neat, right? But on the other side, we have modern fuel injection. This completely throws out that mechanical suction in favor of an electronic brain, the engine control unit, or ECU, which pressurizes the fuel and sprays it with absolute microscopic precision. Let's take a look at the old-school champion first. Carburetors are still super beloved by gearheads, and for really good reason. They're cost-effective, delightfully simple to wrap your head around, and you can usually just rebuild them yourself with a cheap kit. Plus, they're still massively popular in high-horsepower drag racing and classic hot rods, simply because at wide-open throttle, they deliver incredible fuel flow. But, they definitely have their limitations. Because they rely on mechanical physics rather than smart sensors, they really struggle with cold starts, they don't adapt well to high altitudes at all, and they just fundamentally lack the precise fuel delivery needed to meet modern emission standards. Now compare that to modern fuel injection, whether we're talking about port injection right before the cylinder or direct injection shooting straight into the combustion chamber. This system is an absolute master of adaptation. By using sensors that constantly monitor temperature, throttle position, and engine load, the ECU adjusts the fuel spray in real time. For you, that means consistent cold starts, a perfectly smooth idle, and vastly superior fuel economy. But of course, there's a trade-off. When things go wrong with fuel injection, you're suddenly dealing with context wiring, failing sensors, and specialized computer tuning, so it's definitely far more expensive and complex to repair. Next up is Section 3, the ignition battle, petrol versus diesel.
So at this point, the air and fuel are perfectly mixed and just waiting in the cylinder. But when we compare the two main combustion cycles, a fundamental split in engine philosophy totally emerges. Petrol engines, which operate on what's called the Otto cycle, use a spark plug to ignite that fuel. This design is all about prioritizing speed, agility, and higher RPMs, and it operates relatively quietly and smoothly. Diesel engines, on the other hand, they don't use spark plugs at all. No way. They rely entirely on spontaneous compression to ignite the fuel. This specific design prioritizes massive, heavy-duty torque over top-end speed. And that spontaneous ignition is exactly what creates that famous forceful rattle or diesel knock you hear from passing trucks and heavy tractors.
The real secret to the diesel cycle lies in the sheer difference in compression ratios. Think about this. A petrol engine squishes the air-fuel mixture at a ratio of maybe 10-to-1 before sparking it. A diesel engine, though, compresses the air at staggering ratios. We're talking up to 23-to-1. By squeezing the air that tightly, the temperature absolutely skyrockets. So when the diesel fuel is finally injected into that superheated, highly pressurized air, it instantly and spontaneously explodes. No spark needed whatsoever. And that incredibly violent explosion is exactly what generates that unparalleled pulling torque. Naturally, both systems present some very distinct trade-offs. On the environmental side, petrol engines produce lower particulate matter and nitrogen oxides, while diesel engines are more fuel-efficient and actually produce less CO2 per mile, though they do emit higher particulates. But practically speaking, well, because petrol engines run at higher, faster RPMs, they generally experience a lot more wear and tear over time. Conversely, because a diesel engine literally has to be built incredibly thick and robust just to handle those massive 23-to-1 compression explosions, they boast truly legendary lifespans, even under extreme commercial stress.
And that brings us to our final section, Section 4, beating the heat, cooling.
Okay, I really want you to think about those incredible explosions we just talked about, happening thousands of times a minute. To put this into perspective, peak combustion temperatures inside a gasoline engine can hit around 4,500 degrees Fahrenheit, and a diesel engine, that can reach a shocking 6,000 degrees. Honestly, without a way to manage this staggering amount of heat, the internal metal components of the engine would literally just warp and melt together into a useless chunk of metal in a matter of minutes. So the cooling system steps in to save the day. But it's not just some simple fire hose spraying water. It actually has 4 incredibly delicate primary functions. First off, it obviously removes excess heat to keep the cylinder walls at a much safer 400 to 500 degrees Fahrenheit. Second, it maintains a constant operating temperature so the engine runs predictably. But third, and I find this one kind of counterintuitive, it actually works to increase the temperature of a cold engine as quickly as possible, simply because cold engines are really inefficient. And lastly, it cleverly routes some of that absorbed engine heat right into the cabin to provide you with a nice, warm passenger heater during the winter. Now, we all know liquid cooling with radiators and water jackets is pretty much the standard for modern cars. But I want you to consider simpler engines for a second. Stuff like motorcycles, classic stationary equipment, or even older vintage cars. How do they possibly manage this immense 6,000-degree heat without a single drop of liquid coolant flowing through them? Well, the elegance of a direct air-cooled system relies on one very simple principle. The surrounding air is cooler than the engine. So every single component is designed to absolutely maximize contact with that moving air. You'll see thin, raised metal fins covering the cylinder heads, which dramatically increases the surface area for the heat to escape from. Baffles are used as deflectors to push incoming air to the hard-to-reach backsides of the cylinders. Shrouds create this tight little compartment around the engine, and then integrated fans or blowers force massive volumes of air straight through that compartment, constantly stripping the heat away from those metal fins. But here is where we hit upon a truly fascinating engineering truth. The goal of a cooling system isn't actually to make the engine cold. Not at all. In fact, for the best thermal efficiency, an engine actually needs to operate at temperatures closely approximating the limits imposed by the properties of its lubricating oil. Essentially, it needs to run as hot as the oil will safely allow. That means the cooling system is basically a master of delicate balance, constantly walking this incredibly fine tightrope between maximum thermal efficiency and total mechanical meltdown. So when you take a step back and look at the whole shebang together, the perfect rhythmic dance of the crankshaft and the camshaft, the incredibly precise chemical diet managed by carburetors or fuel injection, the intense high-pressure ignition inside those cylinders, and that delicate thermal balancing act of the cooling system, it all becomes so clear.
Whether it's an old-school carbureted V8, a simple air-cooled motorcycle motor, or a modern diesel workhorse, the internal combustion engine is a beautifully orchestrated, highly evolved system.
Which leaves us with a pretty fascinating final thought to wrap up this explainer. Over a century of engineering has perfected this mechanical symphony to a level of almost unbelievable reliability and power. But as our global industries rapidly shift toward renewable energy and electric motors, what role will this highly evolved, incredibly robust internal combustion engine actually play in our future? It's a question that challenges us to look at where engineering has been to truly understand where it's going next.